Good afternoon, ladies and gentlemen. Today we are going to introduce the third generation femtosecond technology, briefly saying the third generation FST. The whole content of this paper can be condensed into the following figure by showing how the third generation FST works. Our final destination is to generate the pulse what we need by the OPCPA chains. But how? By utilizing the a pair of C pulse and pump pulse. And notice that the seed and pump pulse pair can be generated from either only by the pump laser or by the front end and the pump laser together. Each block in the block in this figure represents each block in this figure represent a small topic in this paper. So if we can fully understand the concept of each block and then combine it together finally, we can understand this paper thoroughly. So before our go further discussion about this laser system, let's review the history of the femtosecond technology. The following figure shows the performance of the recorded first generation and the second generation FST and the expected performance of the third generation FST. As you can see in this figure, the average power and the peak power improved following the development of the femtosecond technology. The first generation FST is invented in 1970s and was made by passive mode-locked dye laser. It can generate pulses with duration less than 1 picosecond, contains microjoule energy and megawatt peak powers, and is finally limited by the poor energy storage capability of laser dyes. The second generation FST is based on chirp pulse amplification, CPA, particularly in tight sulfide-based systems with chirped mirror dispersion compensation. It can generate petawatt peak power pulses at moderate average power and gigawatt pulses at approaching kilowatt scale average power levels. And the third generation FST is based on optical parametric chirp pulse amplification, OPCPA, and it is driven by tetrawatt ytterbium laser. It can generate kilowatt average power pulses with terawatt peak power. It also provides a variety of operational modes, which are multi-cycle pulses tunable over several octaves, few cycle pulses at different carrier wavelength, and the multi-octave synthesis of light waveform. Since the third generation FST is based on OPCPA, if we want our system to perform in its best form, we need a better pumping systems. The best pumping pulse duration is of 1 picosecond orders. And a 1 picosecond pumping pulse is the optimized choice, considering the trade-off between optical damage resistance and the work-off between pump and signal pulses. An ideal 1 picosecond pumping pulse is ideal for efficient frequency conversion, and it also makes OPCPA over octave spanning light amplification, which means a wide spectrum of amplification. And among all of these 1 picosecond pumping pulses, diode pumped ytterbium doped thin disc laser is a standout of all. So our discussion will be all around this special disc laser. Here are the recorded OPCPA system performance listed. And as you can see, even the strongest OPCPA system is does not satisfy our requirement for the third generation FST. So only if a stronger amplification system is established are we able to build our third generation FST system. So since we want to build a stronger amplification system, we need a better performing pumping system. So we need to go back to discuss about our 1 picosecond pumping pulse. Several kinds of 1 picosecond pumping pulse have been available. One of these is the flash lamp pump, the passively Morlock nidonium doped glass lasers. It provides low repetition rate and low average power pulses. Another kind of this 1 picosecond pumping pulse is provided by the diode pump fiber slab cryogenically cooled thick disc lasers. These lasers provide a higher average power pulses, but suffered phase shift problem when implemented in CPA. And this problem can be solved by using a large aperture and expensive diffraction gratings. However, among these 1 picosecond pumping pulse, diode pump ytterbium doped thin disc laser provides a cost-efficient and provides a higher energy and higher average power pulses. So our discussion will be all around this laser. A YB-YAG disc laser is constructed by a thin disc with large diameter stuffed with active medium YB-YAG. Its backside is coated with high reflective mirror, and it is attached to a water-cooled supporting substrate. And its front side is coated with anti-reflection medium. And the figure A shows the structure of this disc laser. The pumping light will be delivered in at a specific angle and pass through a well-designed optical path for higher absorption. And with the aid of the water-cooled system, the thermal effect to the optical property is reduced and allow a higher pumping density. And the figure B shows the designed optical path for the pumping light. And since it's a thin disc, it means it has a shorter gain median, which suppresses the nonlinear focusing. Therefore, when the CPA can be implemented with a smaller temporal stretching, which results in the smaller, less expensive diffraction gratings. Also, since it's a thin disc, it means it has a low single pass gain. This issue can be dealt with by using multiple passages through the gain median or serial combination of several discs to increase the gain. And if you want to get a higher energy and power output pulse, just scale up the diameter of this disc. But it will eventually be limited to the amplified spontaneous emission ASE. So if we shine the output pulse into the Morlock ytterbium doped thin disc oscillator, we can generate a carrier envelope phase CEP stabilized pulses. And the Morlocking method can be chosen from current lens Morlocking or semiconductor saturable absorber mirrors. For example, if a current lens mirror is chosen and a pulse with the information in the line 2 shines into this Morlocking system, we can generate an output pulse with the information in the third lines. And it can be served as the million hertz source for near-infrared femtosecond continuum with average power of 100 watt under a control waveform. And the front end, and it also can be served as a front end of the gigawatt to tetrawatt of third generation FSD architecture. So so far we have done the left top side of this laser system, circled by the red circle. And here is the scheme of this Morlocking system. You can see the thin disc oscillator output shines in this system and generate a CEP stabilized full cycle pulses. And if we shine the we put the CEP stabilized pulses into a regenerative amplifiers. We can generate our desired 1 picosecond pumping pulse. A regenerative amplifier is simply put is an amplifier with high quality of pulse energy stability. And figure A shows the schematic of this regenerative amplifiers. As you can see, we see the amplifier with the CEP stabilized pulse, and we stretch it with the fiber Bragg grating. And then we do the amplify and recompress, and the output pulse is shown in the figure B. It has a FWHM of 970 femtoseconds and has a spectral component listed drawn in the green light, and the left top side is the frog trace. And now so far we have done the pump laser part. And now since we have our front end and our pump laser, we can do OPA in this system. We can start our OPA system. Okay, since OPA relies on a temporal overlap of the pump and the C pulses, which means pump and C pulses are derived from the same laser. Now, since if the so-called same laser passing through a regenerative or multi-pass amplifiers, it may induce phase delay problem. Let me make clear with this figure. If your seed generation and the pumping are made from the same pump laser, and then you won't suffer the synchronization problem. But if your seed generation is from the front end and your pumping pulse is from the pump laser, and you will suffer the synchronization problem. And we will introduce an active synchronization system to solve this problem. Figure A shows how this synchronization system works. There is a seed pulse, and you chirp it and do the OPA with the pump pulse. And a specific frequency light will pop out from the OPA and shines on the grating. Then there will eventually be a light pattern distribution on our sensor. Since the distribution is a function of the frequency, light frequency, and the light frequency is a function of the delay between pump and the C pulse. So we can monitor the light pattern distribution and feedback control the delay between the pump and seed. And figure B shows the performance of this synchronization system. You can see the red line shows there is a constant delay between the pump and the seed.
Okay, the next part is part 2, and in this part we're going to walk you through the OPCPA chains in these 3 FST lasers and also its applications, and or you can say it is the main part, the hard part of this OPCPA system. Okay, and first we have to emphasize that you have to pump this OPCPA by 1 picosecond pulses. Sorry, because 1 picosecond pulses they can win over some conventional long pulse OPCPAs and CPAs, and some papers or some articles have already shown that this 3 FST system is best performance under such kind of pulses when it is pumping. Okay, so and here we also show that there are some benefits if you use some 1 picosecond pulses, like your crystals can endure higher intensities, and which can mean you can have higher gain because you're a nonlinear process. Okay, so and also they can be quite thin if you use this structure, and you if you have some short pump window, this will simplify your dispersion control and also the implementation of your CPA. And also third, it can improve the temporal construct of your signal pulse dramatically. Okay, so here's what we think. Because we want to generate a very short pulse, so it means you have to have a very large or very broad spectral bandwidth, and that means your gain bandwidth has to be corresponded to it, so it has to be very broad also. And so here we talk about how they broaden their gain bandwidth by first using different crystal. I think this is intuitive. And second, the same crystal with different orientation, because nonlinear optics is highly dependent of polarization or your orientation. So if you change your orientation, things may be different. Okay. Third, or you can pump the crystal with multiple beams, so you have multiple nonlinear effects doing in the same time. So of course you can broaden your gain bandwidth. And in this paper, we use a 1030 nanometer as our fundamental wave to the first OPCPA chain, and then 515 second harmonic of it to the second chain, and then 343 as the third harmonic of this fundamental wave go to the third chain. So it's a one by one relation. Okay, so we can extend the overall gain bandwidth by this. And here is the basic theory of OPA, and I think it is a kind of nonlinear effect. So you see, you have energy conservation and momentum conservation. If you want to get the best performance of this nonlinear effect, you have to satisfy them both. Yeah, but momentum conservation is a sort of optional. If you don't do it well, it will just decrease your efficiency, not just disappear. Okay, so we're going to talk about how we can adjust our crystal orientation so we can get the best momentum conservation for most of the light, most of the spectrum. Okay, and here's the advantage of OPA. Because I have just told you that these nonlinear effects like OPA, they are highly spectral, highly orientation dependent. So you can just change your pump signal propagation, or even some process like crystal orientation or temperature, and you can modulate both of your central frequency and your gain bandwidth. And this is quite good when you are setting up an experiment. And in this article, there are 3 channels of OPA, as I just mentioned. We have first one, visible light OPA, and it is pumped at 343. I label it in the blue color. And then near infrared NIR, and it is pumped at 515, and I color it with brown. And then mid infrared MIR with 1030 nanometer, and I color it in red respectively. And this formula only shows that this is the gain bandwidth of your OPCPA, and your gain bandwidth can be controlled by, you can see the last term, it can control by your pump and signal propagation geometry, and the big gamma in the middle, it means that you can manipulate it by crystal orientation or temperature, because your big gamma is a function of that. Okay, and here is a generation of our seeding, because we want to get a broadband output. So your OPA must eat in a seeding that is also broad bandwidth. So we use some fiber called gas field hollow core fiber, or HCF, and this is how it works. NIR is produced by the CP stabilization femtosecond thin disk laser after some synchronization, just as we mentioned before. And visual light part is by spectral broadening from the SPM and self-steepening in a gas field HCF. Okay, and MIR is by difference frequency generation. So okay, so you can see that in this figure. So this is how our this is how our NIR comes from. And then we have, from here we start to have some visible light components, and then after HCF we have the whole spectrum of that. Okay, and this is the backbone of our 3FST, which means our 3FST has the 3 key components. First is a high power femtosecond laser, and in our in our experiment, or in their experiments, it's a 100 watt scale curved lens mirror YB-YAG thin disk laser amplifier, and then some multi-octave seed generation as described before, and then we have a 100 watt to kilowatt level amplifier, and with 1 picosecond pulse. And in this case, we use YB-YAG thin disk amplifiers also. And then we try to separate our super continua because we have 400 nanometer to 2500 nanometer of spectrum right now. And as mentioned before, we have to split this super continua into 3 parts: visible, NIR, and MIR, 3 channels. And we do that by using some diachronic beam splitters. And then each 3 channels do OPA separately. And then after doing OPA and they are amplified, we combine them. This is the idea, okay? And then our how do we get these pumps? Well, we can just see in this graph. We do SSG and SFG first. Okay, so we have 1030 right here. After doing SSG, we have 515, and then note that we don't do TH3 or third harmonic generation to get our 343. Instead, we do SSG and SFG. So we got 515 add 1030, and we got 343. This is how we get a third harmonic more efficiently. And this is our setup. So you can see we have 3 OPA chains, and each chain corresponds one of the part of our super continua. And as we mentioned before, OPCPAs are tunable because you can just change your delay, and then you can choose which part we're going to amplify. Yeah, just by using some simple time delay module, we can do that. So, sorry. Here we can try to use. How do we use these outputs? We can just it can be designed to generate some few cycle pulses at a single carrier frequency by some broadband amplification and subsequent recompression. And the application we can be used to attosecond science or some nonlinear optics. And in their simulation and numerical studies, they show that they can achieve right here TL pulse at 12.3 femtosecond at MIR and 4.8 femtosecond at NIR and 5.1 femtosecond at VIS spectrum. And here, after here, we recompress and then combine the 3 parts of continua together. And this is the module, okay, which is here. I circled it with a purple circle. And okay, so they use some diachronic mirrors, so we can try to combine them. And then the conclusion is that the wavelengths can span from 0.45 micron to 2.5 micron, and you can calculate the corresponding TDL pulse with that, and it is like 0.79 femtosecond of pulses, TL pulses, which is in the sub-femtosecond region. And this is the whole part of our presentation. Thank you, everyone.